Hi there, I'm John McMillan, and welcome to this edition of PCB Tech Talk, the podcast where I'll be talking about design tools, the EDA industry, and the questions you're asking. I'll be bringing in special guests from time to time, including subject matter experts and EDA industry leaders. So be sure to subscribe to this podcast. Let me know the topics you'd like to discuss, and if you'd like to be my guest right here on PCB Tech Talk. Let's jump right into today's topic, electrical sign-off. Achieving electrical sign-off more than ever has become a critical part of the PCB design process, and trying to achieve electrical sign-off manually, which is how many PCB designers explore and address them, is time-consuming, it's error-prone, and requires expert knowledge in the areas of SI, signal integrity, PI, power integrity, and EMI, electromagnetic integrity. Today I'll be discussing a methodology for electrical design rule checking that is automated such that anyone can achieve accurate EDRC, electrical design rule check, sign-off, and in a timely manner. So, today I'm not going to talk much about traditional DRC. That is the typical built-in design rule checking in PCB design. That's been around for decades in PCB layout and includes design rule checking and is often referred to as correct by construction rules. Rules that are absolutely necessary and absolutely do improve the overall efficiency and quality of the PCB by reducing time-consuming manual design cleanup of PCB design rule violations and ensuring that the design is correct throughout the design process. PCB layout tools have these traditional standard constraint settings, and in higher-end tools, they typically have constraint management systems that are shared between schematic capture and PCB layout. And front-end and back-end designers, or maybe they are one and the same, use these constraint management systems to define and manage constraints throughout the design cycle. We are most familiar with and used to these basic constraint settings for things like clearances that include trace widths and pad to trace to trace, pin to pin spacings, and so on. You can also manage things like package to package constraints for 2D or even 3D layout that ensure you optimize placement clearances for assembly and manufacturing requirements. But what about constraint settings for electrical sign-off? That is, what about an electrical design rule checking system? In today's high-speed, mixed-signal, miniaturized, wireless technologies, PCB designs are encountering more electrical PCB design challenges than ever. Take compliances, for example. You're having to meet EMC and EMI guidelines, and they have to meet safety standards like IEC standards, EN international standards, and UL standards, for example. Then there are IC chip vendors providing specific PCB layout guidelines, data sheets, even detailed placement, and stack-up reference designs to ensure the component's performance in the end products. And there's a whole host of standard buses like PCI Express, USB, HDMI, DDR, in many different flavors, and the list goes on and on. These are challenging and complicated electrical compliance challenges that require specific SI, PI, and EMI knowledge and expertise to meet performance demands. These electrical design constraints must consider issues related to high-speed design and address issues that impact constraints related to items like same layer and adjacent layer routing or differential pairs, control impedance, net scheduling, match groups, complex, and custom topologies. There, you'll also define things like pin pairs and pin set rules, min and max match length and delay, Z-axis clearances, and so on. And the manual checking for all these electrical constraints and rules, besides requiring specific expertise, is time-consuming and error-prone. In today's fast-paced, high-tech, time-to-market-driven economy, encountering electronic performance issues related to SI, PI, EMI on a fabricated PCB can be costly in many ways. For example, the necessity to fabricate additional prototypes, which adds additional costs, which in turn can impact the product's time to market. I worked for a company that was, and still is, a worldwide leader in IT and networking equipment, with tens of thousands of employees worldwide. There were several ECAD, PCB design groups at different sites worldwide, and they were large. And when you're a big company, there's enough work and also a necessity to justify focused experts for roles. That is, their only job is to focus only on SI, only on EMI, or only on power integrity, PI of designs. But that's not so much the norm, because today, now even smaller companies with only a few or perhaps even one PCB designer are likely wearing many hats. But They are facing the same challenges and the same need for electrical sign-off for their products that the big companies do that have the experts that focus only in those specific areas. So how can electrical sign-off be addressed when you don't have an SI and a PI and an EMI resource on the design team? How can the new high-tech company that has just a few, maybe one or two designers that are already wearing several hats, from being everything from the component librarian to the layout designer to prepping and delivering the PCB for fabrication, meet the electrical sign-off requirements that are necessary to ensure product performance? The type of DRC that can address and even solve this problem today is electrical design rule checking. That is, automated electrical design rule verification that the non-SI, PI, and EMI engineer can use to automate the verification of complex design rules that are not easily simulated, such as rules for traces crossing split planes, T-fork topologies, reference plane changes, and decoupling capacitor placement. Electrical DRC checking that enables you to pinpoint trouble spots on your board that can cause issues. The issues you can encounter with signal integrity, power integrity, and electromagnetic interference and compliance, EMI and EMC, like nets near the edge, coupling to I/O nets, via stub length, and so on. These are some of the items that traditionally consume a lot of time and relied on manual inspection. So let's talk a bit about how this modern DRC, focusing specifically on complex electrical rules, needs to function to accomplish electrical design rules checking and sign-off. Well, firstly, there needs to be a geometric engine in place to perform the calculations, pathfinding, and net topology extractions. This engine must work in conjunction with a 2D field solver that can provide quick and accurate results without the need for preparing device models. I mean, that sounds pretty good, huh? That is an intelligent, complex electrical DRC system that essentially knows what information is required to perform the necessary electrical rule checks. For example, by collecting items such as electrical model assignments, connector definitions, power and ground net definitions, discrete components, and electrical net definitions. Essentially, checks that can be defined with a specific list of design objects like power nets and capacitors, for example. This electrical DRC system must also be capable of filtering by properties like names and component values and part numbers, or any other property, and then generate specific object lists automatically. Then they have to have the associated parameters for each rule, such that they can be edited based on technology and/or corporate guidelines. One of the best comparisons I come up with for electrical DRC system like this is, that is, if you're familiar with DFMA tools like Valor NPI, which, by the way, works with all major PCB layout tools, where it runs built-in manufacturing checks on the post-layout PCB dataset, generates an error report where the system walks you through a preview, that is an image of the violation, coordinates of where the violation is located, with all the details of the DFMA violation that the user or design team needs in order to review and address any issues that are identified. It not only identifies the violation, but also provides you with the correction needed to meet the built-in fabrication requirements. So, what do some of the key features and benefits of this electrical DRC system need to be? Well, of course, having built-in electrical checks capable of performing all the SI, EMI, EMC, and PI checks I talked about earlier. It also needs to have the ability to edit rule parameters based on technology or corporate guidelines. That includes advanced geometric operation. It should also easily access database objects through automation, even a script writing or debugging environment. And it needs a geometric engine that can perform these smart, effective, and efficient electrical rule checks. And of course, I think it goes without saying, a UI, user interface, that's intuitive, easy to set up and use, and a violation reporting mechanism. And like the Valor NPI example I gave, that facilitates both locating and correcting the electrical sign-off violations quickly and easily. Yes, traditionally, electrical DRC has been more of a post-layout step. That is, PCB designers would start the floor planning, then route the critical nets, create power planes, complete the routing, leaving the electrical DRC checking for sign-off, often late or as the last step in the PCB design flow. Finding errors after the fact through manual inspection, that is, after the layout phase, and can require a lot of rework and can take a lot of time to correct and clean up. But imagine with a built-in automated electrical DRC system, the checks can be performed through each step of the design. So you can ensure that design issues are being identified and addressed before you move on to the next phase in the design flow. So for example, before moving on from floor planning to routing the critical nets, you can run electrical rules targeted for the floor planning step before proceeding to the critical net routing phase. And likewise, you can perform targeted critical net checks prior to proceeding to the power plane design phase, and so on, fixing and checking until all electrical DRCs are found and resolved before moving on in the design phase. Well, this type of electrical DRC system exists today, and it's actually a free electrical DRC tool that can accomplish this electrical DRC sign-off. And it just so happens to be a vendor-neutral system. That is, one that works with all the major PCB layout systems, including layout tools from Cadence, Zuken, CADStar, Visualist, CR 3000, 5000, 8000, PWS, Siemens, Mentor Graphics products, as well as ODB++ and IPC 2581 formats. That is, anyone can get a free version of this powerful and fast electrical design rule checking tool that automates the verification process and can fill the gaps where focused SI, PI, and EMI resources are not available, and empower the PCB designers to perform the electrical DRCs that saves hours of error-prone manual inspection, which in turn reduce prototypes, costs, and often critical time to market. This new PCB design industry, and I'm re-emphasizing vendor-neutral and free electrical DRC tool, is new Siemens Mentor product called HyperLynx DRC. Again, it's a powerful, fast electrical design rule checking tool that automates electrical sign-off. Automating electrical design rule checking enables PCB designers to reduce hours, even days of manual checking into minutes or even seconds. It enables users to perform and repeat electrical DRC checks early and often throughout the entire design flow. And since its checks are built in and fully automated, anyone can run these checks without having to have on staff or be an expert in the areas of SI, PI, and EMI. By capturing and preserving design knowledge, it removes the often difficult, unproductive, and error-prone manual checks, things that get overlooked where requirements are unknown or there is a lack of expertise. For more information on how to get your free edition of this electrical DRC tool, check out the show notes. There you'll find a link to the download as well as some additional information related to this podcast topic. You'll also find my email address, so feel free to send me your comments and questions or any topics you'd like to hear me talk about, or if you'd like to be my guest. I'm John McMillan. Thanks for listening, and be sure to subscribe to this podcast on iTunes or your favorite podcast app, and catch the next episode of PCB Tech Talk.